Hey, welcome back. Today we're going to be talking through how to solve a example problem that the College Board has gone ahead and given as an example problem as we wrap up a rotation unit for AP Physics C Mechanics. Actually, this is a good problem to do for AP Physics 1 students as well, and even with a honors physics style class, like a rigorous high school physics class can address this too. There's no calculus here, there's no limitation. You should be able to handle this as well if you're a smart high school physics student. So let's take a look at the problem. So the problem says there's this rod and it's got a pivot point right here. Its length L and it's being held in place initially. You've got a mass of 2m value right here and a mass of 1m value over here at the other end of the rod. It's released from rest, and the question is, what is the angular acceleration of the system the moment it is released? So how do we go about approaching this? Let's go ahead and get to it. Okay, and so the first thing we can do in addressing this problem is to start looking at the forces that are involved here. And I'm just going to draw my forces right on top of the diagram to help us understand what's going on. We have a force due to gravity right here. So Fg2m, we could call it. We also have a force due to gravity right here, Fg4m. That's the force due to gravity for the rod. And then we also have the force due to gravity for the m over here. This is force due to gravity for m1, I guess we could call it. And then there is a force upwards at the pivots, but it's released. So in this pivot right here, it essentially goes away at the moment of release. It's released and the whole thing is going to accelerate, so we don't need to worry about the force going upwards. What we do need to start doing then, therefore, is start to think about the sum of the torques. So I've talked about this previously, but we could use a strategy I call the sum of the torques, or a net torque strategy, you could call it if you prefer. But if we say the sum of the torques is equal to, and then we just add up the torques. Now before we continue, I do want to be careful, because when we're dealing with torques, we have to define our terms. Let's say if we're going to go with a counterclockwise rotation, that will be positive. This is typically how it's talked about. If we have a clockwise rotation, that'll be considered to be negative. So that's what we have going on here with this scenario. Let's apply that over here and think about what's positive, what's negative. So the first force right here, this force due to gravity for 2m, I want you to think, is that going to be a positive torque or a negative torque? Which do you think? Well, that's going to be a positive torque, right? If we were to take that rod and push down on that rod on the left side of the pivot, so to speak, that's providing a positive torque. So we'll just say this is the torque from M2, and that's positive. Alright, the next one, this is the torque from the force due to gravity of the rod itself. That is going to be a negative torque over here. And so we'll say this is the force due to gravity from the rod, as provides that torque over here. And the last one, let's say we also have a negative torque from M1. Okay, and that's the first line for what I call the sum of the torque strategy. Second line is just going to be torque is equal to I times alpha. And then we can just set these equal to each other because they are equal to each other. Just like saying the sum of the forces is equal to mass times acceleration. This is the rotational version of that. Alright, now let's start to think about what these are and start to plug in a little more detail about what these torques are. Remember, torque by definition is going to be r crossed with F. So that r vector times the perpendicular component of the force to that r vector. So in this case, we do want to think about our r vectors. Our r vectors are in fractions of L, so to speak. So our r vectors are in fractions of L. Okay, so for this first term right here, I could just label this as like A, B, and C to try to make it clear which one I'm talking about in which order. Let's think about what we have for A. So for A, we've got a force due to gravity for 2m, so we could say Fg2m times the distance from the pivot point, so to speak. So the distance from the pivot point here, we're going to have L over 4 right here, so that's what we have. Okay, so fair enough. Then we have our second term, so talking about B. Oh, and I guess it doesn't make sense to say we're going to get rid of the pivot point here. We're just going to say that it's released and allowed to accelerate. So let's keep that pivot point here, but we're analyzing the torque. The upwards force, so in other words, I am saying there is an upwards force that's allowed to remain here at the pivot point right here. That actually provides no torque because it is this force from the pivot is exactly right at the axis of rotation. And if it's at the axis of rotation, then it provides no torque. Alright, so let's continue with the problem. This B term over here, let's think about what this would be. It's the torque from the force due to gravity of the rod. So let's just say Fg rod, and let's think about what our distance is. Our r vector is going to be L over 4 as well. Alright, now this actually we need to make into a negative term because it's going to cause a clockwise rotation. Alright, let's do our C term over here. Our C term is just going to be the force due to gravity for the mass times the r vector. That r vector in this case is going to be 3/4 L. Okay, and I'm sort of running out of room, but all of that is equal to I times alpha. Okay, now we can clarify with a little more detail what these things mean and break it down even further. So the force due to gravity for 2m, let's think about that. That would be 2mg times L over 4, that's our first term, minus force due to gravity of the rod. Well, the rod is just mg, that's our force due to gravity for the rod, right? Times L over 4. And the last one, oh, this needs to be negative, again, for the 1m, of course. And you could say, well, what's the torque here? Well, that would be mg times 3/4 L. And that's going to be the r vector here. And all of that is equal to I times alpha. Alright, so our problem is set up better, and that's a key equation right here, but we need to take a detour for a little while. We need to think about what our I value is. So this is the I, the rotational inertia or moment of inertia for the system. So it's just going to be the sum of the rotational inertia for all the parts put together. Okay, and so how do we go about doing this? Well, we're going to say the rotational inertia for the system. Now the rotational inertia for 2m, this is just a point mass right here. So you could say the equation for that is just mr squared, and that's true for this over here. This is just mr squared is the general equation for these two things. So all we need to do here is just think to ourselves, what's the m? Well, that's going to be 2m in this case. The r squared we said was L over 4, so we're going to say L over 4 squared. Okay. And let's continue. So then we also have the second term, the moment of inertia for the rod. Okay, this is tougher, a little bit tougher. And the equation for this is 1/12 mr squared for the rod, but it's also offset. And we've talked about this with the parallel axis theorem. It's going to be mr squared is the offset value. So you want to think about what the offset value is. This whole thing is going to be how you're going to calculate the I for the rod. And I'm running out of room, so let me move this up and we can talk about it. Okay, so we got our A component down. Let's talk about our B components here. So what is our B term going to be in the case of this situation? So the B term is going to be 1/12 ml squared. That's just the moment of inertia for a rod. But then we also have to do this offset component. So this offset component is mr squared is the offset component. So let's think about that. The m is just m, right? And the r in this case is going to be the distance that it is offset in terms of L. We're talking in terms of L's here, in terms of distances, right? So the offset for the center of mass to the axis of rotation is going to be 1/4 L, and we need to be careful, that's going to be squared. So that's going to be like our B term here. And our C term is just a simple point mass. And so if we think about what the mass is at that M1 location, this is the M1 location over here, then that would be just M. And then the R squared, well, for the R value, the question is what's the distance between the point mass and the axis of rotation? Well, that would be 3/4 L, and that is going to be squared. So we're going to add up all of these things. If you do the math and you simplify, I'm not actually going to take the time to simplify all of this right now, but we're just going to say I for the system is equal to 5/6 ml squared. Alright, so we have done that using the parallel axis theorem to calculate the moment of inertia, or the rotational inertia, and also using the concept that if you have a combination shape, like we do, we've got a mass on the end of a rod, and we've got the rod itself, and we've got another mass over here. This is a combination shape, and it's something like a smiley face, I guess. To get the sum of the moment of inertia for a combination shape, you just add up all of the individual moment of inertia values. And if you have something that's offset, you have to use that parallel axis theorem to be able to make that happen. Alright, so I'm going to go ahead and take this and paste it up here with our previous work, and then what we would do is essentially add this in to the I value. And if we did that, it does get a little messy, and I'm not going to show every step here just in the interest of time, but you would end up with being able to cancel out an m out of every term, right? We've got m in every term. If we sub in the I value, this m goes away. And we can cancel out an L out of every term, like we have over here. One of these L's goes away. And so if you do the simplification, you end up with minus 3/5 G over L is equal to alpha. So that's how you go about doing one of these problems. I do want to say I've done videos on an entire year of physics, as well as most of the ideas for AP Physics C Mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.